Okay, so today we're going to start the last chapter of this course, chapter 5, local homology. So in this course we work with commutative algebra, so I'm going to only define local homology of modules or rings, but this can be easily extended to coherent, quasi-coherent Schwirzone schemes. So this is really chapter from algebraic geometry that we're going to do this in this respect, strict settings. So in the first section, we'll just look at the definition and some formal or basic properties. So first steps are quite trivial, just kind of formality, but then in the later sections become a little bit more interesting. So what we have an ideal, so I is an ideal in some ring, and M is an R module. This is the data we're going to. It's like the definition of the depths. You need the module, you need an ideal. So for definition of local homology, you also need a module, you also need an ideal. And in fact, this local homology have relations with the depths. So definition. So first of all, the I portion functor gamma sub I of module M. Well, you can say this kind of set theoretically, which is just the set of all elements in the module M, so elements W, such that this element is annihilated by some power of the united. So this is for some T. This is set theoretically, but we can also rewrite this a little bit more formally. This will be quite useful. This is direct limit of the form the R module I and G. So the last equalities was quite trivial. Here in this form we have exactly these elements W that are annihilated by the I with T, and this limit just one form sits inside another, so this limit is just taking union, which is exactly this. But for computations, it will be important that we can present this as a limit. Yeah, and also let me say this is the first part of the definition, and the second part of the definition, let me say that the module M is called I torsion. If M is equal to the gamma sub I of M. Well, it's kind of the topological notion, as you can see. Here, if you think about this geometrically, well, you know that in algebraic geometry, gamma usually stands for the global sections, right? So here, if I just take the global sections, I just get M, but gamma sub I. This is a global section, so the corresponding coherent sheaf, but supported on the closed subset defined by I. So this is, well, perhaps even in the class of on sheaves, people define homology supported in a closed subset. So purely topological. Okay. About this definition, I have a few rather trivial remarks. I'm not going to prove them because I think they're all very easy.
Global section of restriction of such coherent sheaf on such subscheme.
Restriction to what?
To subscheme. That's defined by
what
I.
subscheme?
Defined by I. Closed subscheme. No, it's not.
Well, because if you can restrict to a subscheme, right? So you take closed subset. You want to say this is a subscheme, so you put kind of the scheme structure of closed subset. This is not a canonically defined thing. right? You can define this I, you can define this I squared, I cubed, etc.
Yeah,
You can do other things. So your definition will depend on the scheme structure,
Yes.
and my definition only depends on the closed subset.
Yes.
So here, this is like essentially I have this limit. Of course, limit is taken over T, and kind of I take a limit over all possible scheme structures on this closed subset. So at the end, this doesn't depend on the scheme structure, it depends on the topology.
Yes.
Do you suppose a massive ring?
Well, you can give this definition and prove some elementary properties in this general setting, that this is any ring, any ideal, any module. But of course, later we'll just take more and more. It will be a finite general module. This will be an interior ring. So first, since this I'm not going to prove, I assume that this, you know this. If you don't know this, do this as an exercise. Since direct limit is exact and home is left exact, gamma I is also left exact. So this remark is important because when we define local homology as the right derived factor of this functor, in particular left exactness implied that the zeros derived factor coincide with the gamma I. 2. No, we can't look at the definition and notice that gamma I is additive factor. And by the way, it's also false from general theory. Any left exact factor or any right exact factor is additive. 3. Gamma sub I is idempotent. Which again follows just from the definition. If you already choose only elements which are annihilated by some powers of I, then if you do this again, you'll get the same module. So, and 4, well, let me write this maybe with formulas. Gamma sub I is a subfactor of the identity factor. Identity factor in the category of modules. Oh, of course, this is just a fancy way to say that the gamma sub I of M sits inside M. Really, this is just by definition. Okay, so these are easy observations. Now let's prove one proposition. So if an R module M is I torsion, then support is inside the vanishing set of I. And moreover, if I is finitely generated ideal, you see this is the first indication that the reasonable theory will be over a Noetherian ring, but we can assume that the ring is not Noetherian, just say that the particular ideal that we work with is Noetherian. Okay, so moreover, if I is finitely generated, M is I torsion if and only if this condition with the support holds. So support of M is inside the vanishing set of I. Okay, and in this finite generated situation, these two conditions are equivalent. Okay, proof. Well, first of all, we can take any module and present this. Well, if you kind of naively, you can write that this is a union of M lambda. Lambda is just some index, and some index extent big lambda. Well, you can as we'll say that this is direct limit of m lambda, same thing. So where m lambda is finitely generated, just a finite for any index. So any module is a union of finitely generated submodules. Well, I think this is quite easy to show. Just choose the generators and consider the module generated by the first and second, third, etc. Kind of this induction by cardinality. Okay. Now we have two simple observations. So M is I torsion if and only if m lambda is I torsion for any lambda in the indexing set, big lambda. And second observation, so say this is bullet 1 and bullet 2. Second observation is that the support of M is contained in the vanishing set of I. This is equivalent to saying that the support of M lambda is contained in the vanishing set of I, and this is for any lambda. So, by looking at these two observations, we can say that without loss of generality, we can assume that M is finite. So if I want to show that if this is I torsion that supports is contained in the view of I, it would be enough for me to do this for finite modules. Okay, so if I know that this is I torsion, so let me say M is I torsion, implies for finitely generated modules that there is number T such that I to the T times M is 0. Oh, well, you know that any generator, for any generator, you can find such T, right? There are only finitely many generators, you can take the maximum of such T. There is no problem here. So, but if the M is annihilated by some power of T, well, clearly support of the M is contained. So support of the M is contained in the vanishing set of I. Okay, so this proves the main claim, and then there is this moreover part. Okay, let me do the moreover part. Let me separate this from the main proof. For finite M, well, we know that for the support of M, we have a formula. This is the same thing as the vanishing set of the annihilator of M. So, a condition that we have now, well, of course, we only need to prove moreover in the other direction. Well, in the first direction, it follows just from the general statement. So, condition that the support of the M is contained in the vanishing set of I. Well, this implies, for example, well, we know that the support is the V of the annihilators, then by the general property of the vanishing sets, if we have inclusion in one direction for vanishing sets, we have inclusion for the ideals, but we just need to take the radical of the ideal. So we'll get inclusion like this. So I is contained in the radical of the annihilator of M. But again, since in this case I is finitely generated, so I is finitely generated, implies that there is T, which is at least 1, such that I to the T is contained in the annihilator, which is what you want, right? So any element of the M is annihilated by some power of T. So this implication is kind of standard observation in commutative algebra, which is just, again, look at the generators at the ideal I and do the binomial formula. Okay.
Why does it to show that E degree T lies in annihilator of M?
Well, because everything here annihilates M, so any element in the M is annihilated by some power of I.
Yes.
So it means that this is I torsion.
Yes.
Okay, definition. The right derived functors of the gamma subgroup are called the local cohomology functors. And of course, if you compute this on a particular module, this will be local cohomology of this module. Okay, now local cohomology functors. So let me write the formula. Notation is hk sub I of M, and this is just the cohomology with the R gamma I of M. Okay. And we can also identify this, that will be important later, with the limit, direct limit of the X groups.
Can we, do we know that limit commutes with taking homology, or since it's exact?
It's exact, yes. Again, using the direct limit is exact. Here, of course, if you forgot how we define the right-derived functors, naively you can think about this. You take M, replace this M with an injective resolution, apply factor gamma I to this injective resolution, and then compute the corresponding homology. Okay. So, as a, do I need to say this? Maybe I say this as a remark, because I think this is, again, quite silly. So, first, H0 I of M coincide with the gamma sum I of M, right? This is already explained. This is because the gamma sum I is left exact. And finally, maybe I just write this in words for shortness. Any short exact sequence of modules produce long exact sequence of local cohomology by the standard reasoning for derived functors with general property of derived functors. Okay, so the next proposition, which is kind of a little bit curious, not so useful. I don't think that we're going to use this quite often, but still. So well, maybe we will use it immediately to see some properties of cohomology. Okay, so let M be an I torsion module. And then M has a unique R hat module structure extending R module structure.
This is completion by I.
Yeah, so here our head is just the completion of the ring R with respect to the ideal head. And since we always have, okay, this is just a remark. So it's I completion. And we always have a canonical map from the ring to its completion. So of course, via this map, this last part of the statement makes sense. Right, so we put on the module R hat module structure such that if you restrict this along this map, you get the standard module structure, which is already given. Okay. Okay, let's start with the case of finitely generated modules. So if M is finite R module, then more or less as in the previous proof, we can claim that there is some number t such that I to the t times m is 0. So I to the t annihilates entire m. So the canonical map from the completion to the quotient of R modulo I to the t gives m and R hat module structure. Well, this is the case of finite R modules. If the module is not finite, so in general, for general module, take this module M, present this as a direct limit of finitely generated submodules, as before, as in the previous proof. Now, H M lambda is R hat module, and so M is also R hat module. We can compute this limit in the category of the R hat modules. Okay, maybe a corollary from this. Let me say local homology or any ideal in any module. There's R I torsion, and hence have structure R hat module. So all local homology are naturally not just modules over R, but modules over the completion of R. Well, the proof is relatively easy. Well, first we can notice that the gamma of I of M, right, so the gamma sub I of M, this is I torsion module. Right, so this is just because gamma sub I is idempotent. Alright, but this is easy observation, but from this we immediately can see that all local homology are also I torsion, right? Well, that is because know how you compute this. You apply this with resolution, right? You apply this functor, and when you apply the functor, you get some I torsion modules And if you take a kernel, this is I torsion, take a quotient by the image, this is I torsion, this is again I torsion.
Why are all terms of the resolution are I torsion?
No, the terms in the resolution is not I torsion, terms in the resolution are injective. Yes, but then to the resolution you apply this functor.
Yes.
And if you apply this functor, you get a complex with the torsion terms.
Yes.
And then you want to compute the homology of the complex with torsion terms, and the homology will be torsion. Subquotient of torsion modulus torsion. Submodulus torsion, quotient of torsion by torsion is torsion. And of course the last part it just follows from the proposition.
Is I torsion model has no higher homology?
That's true.
Yeah.
I think we'll put this in the
So we can, like, for computing homology, we can just take I torsion resolution.
We can, yes. We can use a single resolution. Okay. Right, so as you can see with these general properties we didn't use too much of. It makes sense for any model to satisfy and any ideal to satisfy and generated. Now this one proposition we need some restriction. So I'm going to say that R is not even a ring. We can relax this a little bit. We have two ideals, I and J in R. It's enough to say that these two ideals are finally generated. So R ideals such that they have the same radicals. The radical of I is the same as the radical of J. So then gamma sub I of M is the same as the gamma sub J of M for any R module M. Well, I will say the following, that there are positive numbers and an M such that power of I, or n's power of I is contained in the J, and the other way around, but for the M. Okay, I think this is clear, so just get some number formula. But then we have we will use the following general observation that if I want to compute, let's say, the limit of the home or x, doesn't really matter. It works for the zeroth homology or higher homology, right? If I want to compute this limit. So this can be computed with any, well, let me see, maybe it's so clear, can be computed, well, as the same limit on R, but now I write JT. So notice that the index is now lower, right? So this is just the power of the ideal. And JT is just a family, a countable family of ideals. So this will be the same limit for any family sequence really. Ideals which is, I think the right term is for final for this sequence I to the t. Notice that I to the t is just an example of such family of ideals. But we have a freedom to choose another families of ideals, which are going to go jt, which I will find out. This is the key word in this whole thing that I'm saying, which means the following, that, well, I can find so I to the t, I can embed this inside jt, so equals m, and the other way around, that the jt can be embedded into the I t to the m. So this m are of course positive numbers. So,
But this also should be direct system, yeah? JT. Home from R or quotient JT to the M.
yeah, so any family. Yeah, so I probably want to replace family for any directed system. So directed. Yeah, so this is actually, if you think about this, quite easy exercise in the category theory. Do this. And then, if you have this kind of understanding of category theory, you just apply this category theory result into the situation that we consider. Well, I think it's not hard exercise, so I'm going to leave this to you. Okay, so of course immediately from this we have corollary that this is true for all local homology. So for any k negative and any R module M. Well, that is because if you have two functors that coincide, well, of course the direct functors are always the same. Okay, so this kind of invention of trivial statements about the local homology. Now I think this is the first non-trivial theorem. So let R be an Noetherian ring. Well, I have some ideal as usual. And M is a finite R module. Then, okay, two conclusions. First, the local homology are zero for any k, including k equal to 0, so they're all trivial. So this happens if and only if Im is equal to m. And 2, if this is not the case, so if Im is not equal to m, so there are some non-zero local homology, then the infimum of the k such that hk sub I of m is not equal to 0 is precisely the depth of m with respect to the ideal I. So depth control where we have non-zero local homology, at least if we go from the left, from the below. So in this general setting where we have just an Noetherian ring and ideal, it is hard to say something about the upper bound, right? So there is a statement that all the local homology are zero if you go beyond the dimension of M. That is true. And if the ring is local, not even, then it is known that the at the dimension the local homology are not zero. So hence, in the local situation, the local homology are precisely between the depths and the dimension. So this is what we're going to show a bit later. Now let's deal with this lower bound at the depths. Okay. Well, let's assume that, first of all, that Im is equal to M. If this is the case, I can say that the I to the Tm is equal to M, and that is for any T which is at least 1, just by induction. So then, by generalized Nakayama's lemma, I can conclude that the I to the T plus the annihilator of M is equal to R, still for any T which is at least 1. If you don't know generalized Nakayama's lemma, it is in the notes that in the Google class with the complete proof. Okay, so but then I can observe that if I look at the sum of two ideals, I to the T plus the annihilator of M, and try to apply an element from the sum of the two ideals to the x k of the R modulo I to the T M. What this thing will be? Yeah, because annihilator M annihilates the second argument and I to the T annihilates the first argument, so this is 0. But on the other hand, by the generalized Nakayama's lemma, we know that this is the ring, right? So hence, this is only possible when this X module is actually 0 module. This is 0, and this is true for any k, so any k starting with is 0. Well, if the X modules are 0, clearly the limits are also 0, so we'll get the conclusion that the local homology are also 0 modules. Okay. So I'm kind of proving this together, 1 and 2, so I don't want to write in the proof 1 and 2. So this kind of proves that the first statement is true in one direction. Now, to go in the other direction, I kind of do this together, 1 and 2. I suppose that the Im is not equal to M. And then I choose a maximal M sequence in the I. So let x1 up to xd inside I be a maximal M sequence. So in particular, assuming that the depth is equal to the d. So the goal is to show the following. So we show by induction of the depth d two things. So that hk sub I of M is 0 for any k less than d, and also that the ht sub I of M Well, I think you agree with me. If we can show this, right, the conclusion of this statement, then we finish the proof of 1 and 2. Okay, so let's do the induction. The base of the induction is d is equal to 0. So let me say if d is equal to 0, well, it means that there are no regular elements inside I. So every element is a zero divisor. So let's say that then I is contained in the set of the zero divisors of the module M. So, but then the home from the R module I to the M is 0. Sorry, is not 0. Is not 0. So there is element W in the M such that IW is equal to 0. And of course this W is not equal to 0. Let me say W is in the M minus 0. So this means that the H0 sub I M is not equal to 0. I think everything is more or less trivial, maybe except this application. If I is contained in the zero divisors, then the home is not equal to 0. Do you see why this is so?
Why
Well,
you
it's something like for Nazarian finite zero divisors and union of associative ideals.
Yeah, you can say it like this, but in fact,
Why you can use the least formula for depth?
we can do this, but we also proved it a statement. I think this was the very first statement in the section 1.2. Then we characterized that when such homes, actually x, are vanishing. Well, they are vanishing precisely for the indices strictly smaller than the depths of the second argument. So here the depth is 0, hence home has to be not 0. So I'm just using what I proved before in the beginning of the course. And I need this statement again for the step of the induction. So this finishes the base. Now let's do the step. If D is positive, well, the standard thing is to look at the short exact sequence 0, M, well, say x1, first element in the maximal regular sequence, M1, which is by definition M modulo x1M. Okay. So then x k r modulo I to the tm is equal to 0 for any k less than d. And of course for any t starting with 1. So this is again that statement, first statement on the section 1.2. Right, the index is less than the depth of the second argument, and this is supported on the ideal, then such x is 0. But again, if the x does 0, local cohomology are limits of such x. So immediately from this we see that hki of m is 0 for any k less than d. And this finishes the proof of the first plane.
Why such x are 0?
Why what?
Such x.
Again, I'm saying that I'm using the statement from the beginning of the course, and if you want to find the statement, this kind of theorem with the following four conditions equivalent, this is the first statement in the section 1.2, where we prove that the vanishing of such x is equivalent to saying that the up to some number d is equivalent to saying that the depth of M is d. And the equivalent statements where you can take R modulo I, you can find, you can take any module as the first argument supported on I, and this is true not for any module supported on I, but for some module supported on I. So there was that data about this.
And if the depth of I is d, then the depth of I in degree t is also d.
sorry, I don't understand. This is for k less than d, right?
Yes.
So this gives us the vanishing of the local homology for k less than d. The non-vanishing result we still have to prove.
Yes, but for ideal I. And here we have ideal I in degree t.
No, it's for any model that have support that contained in V of I.
So this will be true if the first argument is supported on the v of I. In particular for I to the t, this works for phi. Okay, so this is the vanishing result, and finally the non-vanishing result. Well, the non-vanishing result follows quite easily if we look at the long exact sequence for the local homology. So let me say maybe we have hi with the index d minus 1 over m. Then they will be mapped to the h with the index d minus 1 sub I of the m1. Then there is a connecting homomorphism to the h g sub I to the m. Maybe this is enough. Let's see. Okay, so we know that this is 0, right? This is for the d minus 1. Well, d minus 1 is less than d, so this is 0. In fact, we have, and by induction hypothesis, this is not 0, right? So this is 0. It means that this non-zero sum module is embedded here, right? So hence this is also not 0. End of the proof. Okay. Okay, so theorem. This is the Mayer-Vietoris sequence for local cohomology. So let R be an Artesian ring. I and J are two ideals. And M is an R module. So then there is a long exact sequence. So where we have homology for the intersection of all the ideals. Well, they are related with the cohomology for the intersection. They are related with the cohomology for the sum of two ideals. And the sum of cohomology, so hk sub I of n plus hk sub j of n, and again hk I intersect with j. And then you continue. Sum of cohomology and the cohomology for the intersection. And this indeed looks like my Vietoris sequence from the algebraic topology. Well, if you look at the let me read this more accurately. So I intersect with J. Right, so if you look at the intersection of the ideals, this is the union of the corresponding closed subset. If you take the sum of the ideals, this is the intersection of the closed subsets. So it's kind of like Mayer-Vietoris, but for the closed subsets. Okay, so for the proof, first of all, we look at the following well-known short exact sequence: 0 R modulo the intersection of two ideals. So in this case, the intersection is just the I to the n and j to the n. Sorry, two ideals are I to the n and j to the n, but this is not important for this short exact sequence. This just works for any two ideals. Okay, so if you don't know this, again, n is not important. Think about the k case n equal to 1. So this kind of generalization of the Chinese remainder theorem. Chinese remainder theorem tells us that if the two ideals are co-prime for two ideals, then this is just a ring R, so there is no this term, so there is an isomorphism of this sum and the quotient by the intersection. But if the two ideals are not co-prime, well, you can write the corresponding short exact sequence. I'm pretty sure that this short exact sequence are in the notes, but maybe as an exercise. Okay, for this we can look at the corresponding long exact sequence of x. So get x k r modulo I to the n plus j to the n m. Next k. Just straightforward application. You just need to know, well, need to remember that when the second argument is fixed, this is contravariant functor, so get the direction of arrows correct. That's probably the main part in this computation. Okay, so now I want to go to the limit and see that in the limiting case I'll get exactly the long exact sequence that I want. This requires kind of 3 little computations that the limits are correct. Well, first of all, we can notice by the binomial formula that the I plus j, if I take the sum of these two ideals, raise this to the power 2n minus 1, then this sits inside I to the n plus j to the n, which is again clearly sits inside in the I plus j raised to the n. Hence, by this argument with the cofinal systems, we can conclude that the hk sub I plus j of m is isomorphic to the limit of the x k r modulo I n plus j to the n m. That's not really readable. I to the n plus j to the n. So this means that this first limit for the I to the n plus j to the n is the correct limit that corresponds to the sum of two ideals. Now, there is one trivial case. Well, for the direct sum, it's more or less immediately clear this is the case. And for the last one, we need to do some computation. So let me well, the result follows from the Artin-Ries lemma, but to see how exactly this follows, let me formulate Artin-Ries lemma in the notation that I'm going to use in this computation. So Artin-Ries lemma, of course, this works under the assumption that R is not even, that's important, but this says that if you have L is a submodule in the finitely generated module M. And so then there is number S, positive, such that I to the D, L intersect with the ISM is equal to the L intersect with the I D plus S M. And that is true for any D non-negative. Again, you can find the proof of the Artin-Ries lemma in the notes on the Google Plus. There's a little bit more general statement about filtrations, but if you apply the filtration of the module, which is just of this form, I to the S times M, and then this is what you get from the Artin-Ries lemma. Now, I want to apply this in the following situation. I want to take L to be J to the N, and I want to, of course, take M to be just equal to the rated part. Okay, so then what I'll get is the following: I to the D times I S intersect with the J to the N is equal to the I D plus S intersect with the J. Right? So this is the formula that I need. So let's now do the computation. I to the N plus S intersect with the J to the N plus S. Well, first of all, by trivial reasons, this is contained in the I to the N plus S intersect with the J to the N. Right? The higher the power, the smaller the ideal. So clearly this is just sub-ideal with the J to the N. So this is by trivial reasons. Now, on the next step, I want to apply the Artin-Ries lemma in this particular form for the two ideals, and rewrite this as the I to the N times I to the S intersect with the J to the N. Just another kind of renaming the indices to get the result. D is equal to N now. And finally, again by trivial reasons, this is contained in the I to the N, and of course this intersection of the two ideals is contained in the J to the N, so times J to the N. Which again, easily can be seen that is contained in the intersection of the I and J raised to the N. So by induction you can do this. By N equal to 1 is clearer than do the induction. Okay, right.
We need to
Yeah,
another direction.
yeah, and the other direction is again, there's nothing really to show. Clearly, this is contained here. So together, this whole two inclusions show that this is the cofinal direct system, and hence the local homology with the index A for the intersection of two ideals can be computed as the limit of the x k for the R module on the n intersect with j to the n. And finally, I want to say that clearly the sum hk sub I of m plus hk sub j of m. Well, essentially, I'm just using that x is additive in the first argument, and that the direct limit is exact. So then we can identify this limit of the text. R modulo I to the n plus R modulo j to the n, and the second argument is n. So that's the end of the proof. This is quite useful statement. Well, in what I kind of prepared and how I want to go, I'm not going to use this statement quite often. I'm going to derive the main results from the other statements. But it is possible to go to kind of choose different road and derive almost everything about local homology just from this sequence. Okay. So this is the last statement I want to prove in the first section about the basic properties of local homology. And now I want to go to the second section, so 5.2. I'm going to call this local homology and Czech complex from topology, or geometry. Algebraic geometry is also use Czech complex. So in fact, secretly, local homology are just Czech homology. So in this section, we need to see why this is the case. Okay, so
I want to ask, is there some type of homology for open spaces, algebraic open subspaces? Like restriction for open part.
well, this is more or less the local homology.
Why?
Well, you're supposed to do this in the last problem in the assignment 4.
Ah, okay.
So there's an exercise about algebraic geometry that exactly answers your question and a little bit more. If you know some complex analysis, there is Hartog's extension principle, Hartog's extension lemma, you can prove this in algebraic geometry. You can prove this indicated in the class problem. Okay, so I want to fix notation. I want to consider finitely generated ideal. Well, maybe the ring is not Noetherian, but the ideal that I consider is definitely finitely generated. And I'm going to call generators x1 up to xc, c for codimension. And then I want to introduce the sequence raised to the power t, which will be just by definition the sequence x1 to the t, xc to the t, just notation. And then the lemma is that we can compute the local cohomology of M as the limit of the x. But now, instead of using the kind of the power of the ideal, I look at the ideal which is generated by the powers of the generators. Okay, so the proof is the same as before. Well, x ideal generated by x to the t is contained clearly in the ideal generated by the powers. No, just again, I'm just checking that. Not really checking, I'm more or less I'm just stating that the condition that this is cofinal are satisfied. And leave it to you to check this.
What is D?
No, d is just some positive number.
Oh.
Well, again, just an exercise in binomial formula. Okay. Now we do the following. We consider inverse system.
Is the first statement true? Because I can consider an ideal, for example, in
Does this fix?
so we find some C.
Yeah. If we can do this with some positive integers c and d, This is what we need for the cofinal system.
Yes.
Okay, so let's consider inverse system of Kazoo complexes. Okay, so here I have Kazoo complex for the sequence with the kind of index t plus 1. Oh, it means that I take this generator of the ideal, raise them to the power t plus 1. So then there is the augmentation map. Let me call this augmentation map epsilon. I don't think that we fix notation for the augmentation maps. So this is epsilon t plus 1. So this is to the R modular sequence x raised to the power t plus 1 and then generate the ideal. Okay, so then there is Kazoo complex which works exactly the same but for the index t, not t plus 1. So augmentation map is epsilon t. Okay, so here between the quotients there is a canonical map which is just a multiplication of the x1, x2 up to xc. And this can be lifted to the map of the Kazoo complexes. So let me call this phi with a bullet and index t. And moreover, we can explicitly define this map phi. So I can say that the phi with the index 1, okay, there are two indices, there is lower and upper, so upper is t and the lower is 1. Well, since the Kazoo complex has an algebra without differential, this is just an exterior algebra. It would be enough to define this on generators. So I'm defining this on the basic vector EI, which is one of the generators of the exterior algebra, to be just xi times EI. And this is of course for any I between 1 and c. And then if I want to extend this to the exterior algebra, well, I just take the corresponding exterior power. So this is, these two formulas give me a definition of the map phi. And I leave as an exercise to check that this is a commutative square with this definition of phi.
What is the second map? This vertical map.
This one?
Yes.
This is multiplication on this element, on the product of all generators of the ideal. Okay, so this is the inverse system of the Kazoo complex that we consider. Well, in fact, that this augmentation maps won't play any essential role. What's important that we have this kind of inverse system of Kazoo complexes, and the maps between them are defined by the following two rules. And we also have kind of dual situation, since this is for homological complex, and we can also do for the cohomological. Let me call the corresponding maps beta. So now this again says two indices t and some upper index. So this will be from the homological Kazoo complex, the sequence x to the t, to the Kazoo complex, the sequence t plus 1, x to t plus 1. You just have to take a dual, the map will be in that direction. Okay, definition. The stabilized Kazoo complex or sometimes the same object is called extended Check complex name for the same thing. If you kind of prefer algebra, you're probably going to call this stabilized Kazoo complex. If you prefer some kind of topology and geometry, you can call this extended Czech complex, or just Czech complex. I'm going to explain in several minutes why this is called extended or just Czech complex. Well, it's the following. If you kind of want to call this stabilized Kazoo complex, the first notation is preferable, and the x to the infinity, second argument is sum modulo m. If you want to use Czech notation, you just write C, standard check mark for the Czech, for the sequence, and the modulo m. But anyway, doesn't matter what notation you prefer, I'm going to use mostly first notation. This is by definition the limit, so direct limit over T of the homological Kazoo complexes x to the T, and the second argument is the modulo m. So this is stabilized Kazoo complex, so extended Czech complex if you wish of the modulo m. So to say it somewhere for the modulo m. Okay.
And is there some for homological Kazoo complex?
Well, you can try to do this, but this is what will be important to us because this is exactly what is related to the local homology. And the dual version, I'm not so sure that this is directly related to the. There is a notion of local homology that probably we won't going to discuss in this course, but you can define them. You can ask the question: is it true that there will be corresponding relation between local homology and the kind of limit? So this is the inverse limit for that sequence. But I don't think that this is a correct statement. But I never checked this actually, and I never seen this in addition. Okay. So before we prove anything, we can look at the very simple but useful observation that, okay, so there is this stable Kazoo complex, which is the corresponding limit, let me write this limit, and here for the Kazoo, homological Kazoo complex, with coefficients in the modulo m, I know that I can write this as just that tensor product with the modulo m. And I know that the limit commutes, so direct limit commutes with taking tensor products, so I can identify this with the k. This is not t, this is infinity. Tensor product is.
Why they commute?
Well, the tensor product we know by the tensor homojunction is the left adjoint factor, right? And any left adjoint factor preserves colimits. Remember that the direct limit is actually colimit. So by the general categorical nonsense. And exactly by the same argument, I can write here not a module but another complex. Potentially I can define the notion of the Kazoo complex with the coefficients not in the module but in the complex. For example, I can do this with another Kazoo complex. And if I do this, I'll get the following. And then the stabilized Kazoo complex is isomorphic to the tensor product of the stabilized Kazoo complexes, but each of them is just for one individual element. Right. So we kind of use the same logic for unstable version of the Kazoo complexes. We can do this for the stable too. Okay, now lemma. With this formula, it will be enough just to understand what is the stabilized Kazoo complex for just one element. Explicitly, what is it? So I claim that this is the following thing. I take stabilized Kazoo complex for some element x. There's only one element, so there is no limit of this x1 or something else, just x. And I can identify this with the complex which has ring R in the degree 0, localization of the ring R at x in degree 1, and the rest is just zeros. So it's very easy complex. And yeah, so now let's prove this. Maybe it is useful to kind of look again at this inverse system, but in this very special case where we have just one element, and see explicitly what I have in mind when I talk about that thing. So let's say for homological complexes, let me just write, I don't have space here, well maybe I try to write here. We have the following: 0 or multiplication on the x raised to the power t plus 1 or 0. This is just the Kazoo complex for the element x to the t plus 1. It's not very visible, sorry for that. Now here, this is multiplication on x, or here multiplication on 1, and this is x. So I'm just writing two Kazoo complexes for t plus 1, for x to the t plus 1, and for the x to the t. And the corresponding maps phi. So this is kind of phi 0, and this is phi 0 is 1.
Why phi 0 is 1?
Oh, by definition. This is supposed to be the exterior degree, 0, 0 is exterior degree of some map. It's 1 by definition. But you can also notice that even if you don't have that general definition, this makes sense for this particular case, right?
Mm-hmm.
So clearly the diagram is commutative, clearly these things are Kazoo complexes. And clearly you can extend this to get the inverse system of Kazoo complexes of one element. It's for anything. Okay, but here of course in the definition of stabilized Kazoo complex, we need to take this situation and dualize. So let me say dually. So dually, we have 0, or this is multiplication by x to the t. So this is 1, or x to the t plus 1. X. So this is what we get if you take home into R. Okay. And now we only need to take the direct limit, right? So it's kind of the two terms in the inverse system. And what will be the direct limit? Well, first of all, if we take the direct limit of this thing, R1, 1, etc., what's the result?
R.
Yeah, this is just R. And for the second one, R, x, etc. So what is this? Yeah, it's just localization. Let me again leave this as an exercise. It's a quite simple exercise in co-limits. But if we have these two things, that's exactly what we need to finish the proof. Yeah, and it's also time for
Why is the map such? It's the same map as localization.
what much?
Well, will be when we take co-limits of the complex, we still have we have co-limit of map.
You're asking why? Well, it's more or less you get this when you compute this directly. The question is, if I understand correctly, is that here when I write this, I assume this is kind of canonical map from the Rimke localization, and you ask me why exactly this is the map.
Yeah.
Well, it's more or less follows from the computation that this is R localized this. Домашнее задание вчера повесил, я понял, что у меня немножко есть. Одна задача очень простая, на самом деле я лекцию сегодня зову. Поэтому это у меня другое. И еще одну я сегодня придумал, пока сюда ехал, как прохнуть есть занятная задача, связанная с всей этой теорией. Ну, я, когда у меня, я напишу, что я могу их повесить. Там вот есть задачи, руками библиотеки, там коммутируются взятием дополнения, в общем, как бы они очевидно. Не вообще коммутируются взятием любого плоского расширения, а помните, вы жаловались на 15-ю задачу в прошлый раз? Я над ней подумал, там все правильно, все работает, и действительно это не сложно. Хотите подсказку такую?
13, ну давайте.
Ну, там бывает. Ну, там очень ключевое место, надо доказать вот такое, что если у вас есть какой-то модуль, нельзя доказать упражнение, но с конечной плоской изометрией.
Ага.
Можно сказать, что у меня есть конечная эффективная изолента.
Да, как это делать?
Можно, например, взять такое, взять этот модуль, ну, точнее, взять даже его изоленту, умножить на эффективную изоленту для кольцевого кольца.
Для самого кольца.
Да. Смотреть, что получится, что это за комплекс, какие у него технологии, и потом из этого комплекса нужно просто явным образом построить эффективную изоленту. Исходного модуля и еще конечная.
Ой, какой ужас. А в обратную сторону.
А в обратную сторону, если подумать, это вообще практически не доказательство. Да, там есть такой, как более творчество использование Homological. Там надо иметь, что один комплекс в одном направлении, другой комплекс в другом направлении. Когда вы переносите, у вас направления перемешаются.
Что?
Ну, плоское восхождение.
Не, я понимаю, я вот до этого об этом не задумался, я говорю, сейчас реально в разные стороны, что там вообще произойдет, там даже будет получаться какой-то бикомплекс, в котором там вниз и влево. Ну да, я понимаю, я просто думаю, это что...
Ну, возможно, будет комплекс, который будет естественно писать на каких-то степенях.
Нет, просто дифференциал там разве правильно, хорошо, определен, корректно.
Но у вас например, другое, если ну, способный комплекс потенциал, и там степени плюсами, то есть проблемы.
В смысле мы просто ставим вот всю индуктивную резоленту, там мы ставим в плюс, а всю плоскую вниз, вниз. Ну да. Ну да, тогда да. Ага. Ну,
дальше можно понять, какие науки, там чуть-чуть пообрезать, посмотреть, что можно из этого извлечь на самом деле эффективную изоленtu на одном уровне. Ну и чтобы вам как бы было возможность сделать работу над ошибками, я такую же задачу включил в последнюю встречу тоже, только еще сложнее. Задача номер 5 называется.
Ясно. Да, можно, кстати, спросить вас, а вот там, потому что мне, например, поставили это не полностью то, что я записал. А где можно посмотреть, в чем ошибки?
Разве не полностью?
Ну, у меня 110 стоит, а я вроде 13 задач решил. Ну там, я просто не знаю, может вы 13-ю не за 2 считали?
Нет, 13-ю, ну, я мог ошибиться, конечно, но вообще считал за 2. Я большую часть людей писал уже такой список задач, сколько я записал выбрал.
Ага. Куда вы их писали?
Вот прям туда, там, в комментарии.
Комментарии? Вот у меня, по-моему, нет ничего в комментариях. Ну, сейчас проверю.
То есть, если как бы, я почему-то определялся, я не хотел какую-то задачу ставить полный балл, я обычно писал, что за эту задачу. По-моему, это вы доказывали, кстати, задачу там про взятие вариантов Z по 4Z. Да? И вы доказали, что это полный поле вот отсюда.
Сейчас Z по 4Z. Инвариант, да.
Оно не понял.
Оно не понял?
Я написал в комментариях, что это, соответственно, не понял поле, я это не засчитываю.
Да, но вы не написали это в комментариях.
Ну, нет, оно в других комментариях. Там можно выделить кусок и к этому куску приписать комментарий. Я такое сделал.
Разве он тогда не должен как-то это... Вот я вижу даже какие-то.
То есть это вот это я не засчитал. А все остальное полностью засчитал.
Странно тогда, можно сказать. Да, вы видели, да, типа таким. Просто вот единственное выделение этой задачи, это вот там просто желтым помечена сама задача.
Да.
Это вот все, да?
Я так не планировал сделать. Ну там просто, у вас на самом деле там первый шаг уже там первый шаг у вас какая-то правильная.
Я говорил, что там, ну, просто там, ну, кольцо инвариантов, оно домой, значит там любой элемент регулярный.
Да, это несомненно верно, но то, что нам под концу просто выполняет. Дальше следующий шаг у вас уже неверный.
Когда я факторизую, я там факторизую и говорю, что оно равно кольцу инвариантов другому.
Да, ну, в общем, в простой характеристике это неверно. Потому что это я не засчитал, все остальное, конечно, я засчитал. Потому что все равно не сходится.
Мне кажется, да, тогда должно быть 120. Сейчас
у вас есть какие-то, все эти баллы, я суммирую просто в уме. Поэтому там вполне можно сделать ошибку. Если вы считаете, что у вас где-то что-то неправильно рассчитано, напишите мне письмо. Если что, там в Google классе там почта длина, и мне нужно написать письмо там, с Google класса, ты просто написал Gmail. Сюда нужно написать письмо, и можно как комментарий целевать, что получается. Если вы думаете, что там что-то неправильно, это суммирно,
Я сейчас посчитал, все правильно, какая утка. Что-то странно, почему-то я думал, что я больше решил. Потому что 14 всего. Ну да, конечно, да, тогда все хорошо, да. Точно, я что-то подумал, что 15, тогда должно быть больше, но нет, так все хорошо. Сейчас уже, в принципе, время, да?
Да, еще, кстати, вы заметили, что есть специальные сессии, и у нас остается действительно одно занятие. 19-го у нас в расписании стоит экзамен. Ну и у всех. По всем спецкурсам на неделю уже экзамен.
Блин, какой ужас.
Вы, наверное, еще не видели расписание сессии, может, она просто не до конца утверждена. Но преподаватели вообще рассылали, вот эта неделя, которая у нас 18-го, там уже экзамены стоят по спецкурсам.
Странно, на самом деле.
Поэтому семинар по Homological у нас отменяется, но сегодня 2 лекции, в следующий раз 2 лекции.
Мы же можем просто взять и провести 18-го семинара. Ну, в смысле, просто взять и провести пару.
Ну, мы можем, на самом деле, возможно, не то, чтобы я прям очень хотел.
Окей.
Я думаю, что я немножко ужмусь, адаптирую, кое-что рассказывать не буду, и за 4 лекции по содержательной структурной блоке я, наверное, не успею вот эти теоремы обращения норм.
Сейчас 4 лекции, включая сегодняшнюю, да?
Ну, сегодня это следующий неделе.
Ну да, просто. Это в смысле, вы уже ужались, уже.
Да, ну я вот результаты обращения норм, расходов Павлова и теоремы связанности, расходов всяких других людей не успею, а все остальное я думаю, что я успеваю. Да, давайте продолжим. Okay, so from this observation, there are 2 observations about the reducing to the tensor product of such simple stabilized causal complexes and the last lemma. We can immediately derive corollary that in general stabilized causal complex has the following structure. The complex has 0, R, and then we have a sum from I between 1 to C of the R localized at the xi. So the general term will be direct sum over indices, say I1, which is less or equal than I2, less or equal than IC, so, no, IP, which is less or equal than C. So kind of multi-index, like in the exterior algebra. And R is localized at the X I1, X IP. So this is term in degree P. And finally, the last term is just localization of the ring at x1, xc. After that, we'll get zeros. So this is just the result of a tensor product of those small complexes. And well, we can do this more generally. So, and more generally, since if we want to compute the stabilized causal complex with coefficients in the module M, how can I just take this causal complex and take it as a product with M? So get 0, M. So the only thing I need to do is just replace R with the M. And now if you look at this, this looks more or less like a causal complex, right? So if you, for example, if you forget about this M, so this is just the sum when you restrict, well, the open cover that we consider in this case is just UI, right? So I mean, this is a, of course I don't need to prove this is clear. The open cover is UI, which is the complement with the spec R minus the vanishing set of the xi, so the union over I of the ui give me the spec R. Spec R minus the vanishing set of the. So this is the open cover for the complement to the vanishing set of the ideal. And if you just use the topological definition of the Jack complex, you get precisely this for the corresponding shift that corresponds to M, except we won't see this M. And for this reason, this is called the extended Jack complex, because you add this kind of mutation in the form of M. Okay. So now definition. We can define the Jack homology of a module M. Well, this is H, A, depending on the sequence X. And well, this is, by definition, just the homology of the corresponding stabilized Kazoo complex. And using the exactness of the direct limit, I can as well write this as a direct limit of the homology of the usual Kazoo complex for the x to the t. Okay. So essentially, what we need to prove next is that this Jack homology are precisely the same thing as the local homology. It is not so easy to prove, it requires some work. And before we do this, I want to formulate the lemma. So, lemma, which actually just to remind you something that you already know. So let R be the theory. R. Take some prime IU, so say E in the spec part, and set E to be the injective half of the R module P. So then, about this E, we have two relations. So first, if you localize this E, you still get E, and two, then the local homology of this E for the ideal, which is the prime ideal P. So this is E. This is E for the zero local homology for the gamma, and the higher local homology are all zero. Okay, so this is lemma. So let's prove this. Well, in fact, I actually proved statement 1 when we discussed the structure theorem of the injective modules of Noetherian rings. But maybe let me briefly remind you the computation. So we take x in the R minus p in the multiplicative system. We consider map phi, which is just multiplication on x from the injective half of the R modulo P to the injective half of the R modulo P. So this is multiplication on X. I even keep the same notation that we used when we actually proved this statement. Then the kernel of phi intersect with the R modulo P. Well, by definition, these are classes T plus P. So class in the R modulo P, such that X T plus P is equal to 0, but I claim that this is 0 since right, if we have x times this class is equal to 0, it means that the x times t is actually in P. We know that x is not in P, but we choose it this way. So using that P is prime, we conclude that the T is in P, but it means that the class that we considered to begin with was a zero class, right? So this intersection is zero, and since we know that the map RP which embeds this into injective hull, this is the essential extension, we can conclude that the kernel of phi is zero, hence the injective hull of the R modulo P coincide with the image of phi, and noticing that injective hull of the R modulo P is indecomposable we conclude that phi is isomorphism. I'm just repeating the argument that I've done before. If you can find this argument as a part of the proof of the structure theorem of injective modules over a Noetherian ring, that this is a direct sum of injective hulls for some prime ideals. So this, yeah, and I actually proved part one, right? If I know that any element in the multiplicative system acting as an invertible element, it means that the localization of this multiplicative system doesn't do anything, so it's isomorphic to the given module. Okay, second part. So let W be an element in E minus 0, so a non-zero element in the E. Let's set I to be annihilator of this element W. And then R modulo I is embedded into E. This is some module, right? Just sends the generator of this cyclic module exactly to the W. Okay, but then, since this is a submodule, associated primes of the submodule is a subset inside the associated primes of the module E, and we've done a computation that shows that the associated primes for the E is just a simpleton with a prime ideal P. Well, and this is a non-zero module, hence this is not zero set, as subset set with one element, so this is only possible if the associated primes of the R modulo I is precisely the set that contains one element P. Okay, now the radical of I, which is clearly, by definition more or less, is the same as the radical of the annihilator of the R modulo I. Well, just annihilator of the R modulo I is precisely I, so this is silly. But for any module, in this case, I'm talking about module R modulo I, the radical of the annihilator of the module is precisely the, no, it has to be finally generated module, but R modulo I is finally generated, of course, it's cyclic. So the radical of the annihilator is precisely the intersection of the associated primes. Here there is only one associated prime, so this is just P. Okay. Now, using that everything is finitely generated, the ring is Noetherian in this lemma, I can say that there is number n, which is at least 1, such that p to the n is contained in the I. Or in other words, p to the n times w is 0. So, what I proved in this statement is that any element in this injective hull is annihilated by some power of P, right? Now you can go back to our discussion of the matrix duality, and at some point I was writing for the special case where this P was a maximal ideal, I was writing this P as a union of the, I was writing this E as a union of the UN, such that elements in the En are annihilated exactly by the power n of the maximal ideal. And that proof was incomplete. Here, this is the completion of that proof. The argument with the associated primes and the radical. You actually gave the same proof when we discussed that. So this is just the same proof, but not for maximal ideal, but for any prime ideal P. I'm kind of essentially the reason why I'm telling you this proof right now, just kind of fix this a little bit incompleteness in the proof of the matrix duality. But well, there was a kind of claim that I can present E as the limit of the En. The proof was incomplete, and this is the completion of that proof. Okay, but here in this situation,
And this statement was that where is that E is limit of En?
well, that was in the matrix duality.
In the beginning of matrix duality, or is it?
I don't remember exactly the statement, but it still feels like it was more back in the beginning of the matrix duality. But anyway, if whenever you see when you see that you need to show something like this, and one of the proofs, here is the missing argument.
Oh.
Or if you can say this is a generalization, not for the maximal ideal, but for any prime ideal. Okay.
Yeah, exactly. What we proved in the end, I just didn't get.
Well, at the end we proved that whenever you take a non-zero element in this injective hull, you can find the corresponding power such that this, well, power n such that p to the n is annihilating this element w.
So it's torsion.
Yeah. So in particular, we can say that E is p torsion.
And why is right.
Well, and if the p is p torsion, that's exactly how we get to. Okay. This is the number. And now proposition. So I'll continue to assume that R is not even. So let R be not even rig. So then, no, the same assumptions as before. M is finite. Our module might be not necessarily finite. Let's do I need the assumption that M is finite? We will see this in the proof. Okay, so then the first claim is that the zeros Chekhov homology of the sequence X. We call that this sequence is the sequence that generate ideal I of M is isomorphic to the zeros local homology of M 2 for any short exact sequence of modules 0 M prime M double prime. There is a long exact sequence of Chekhov of homology. Well, Chekhov homology are not the derived factors, so it doesn't follow immediately, but it's not very hard to show. So let me just write the long exact sequence. So Chekhov homology index k for this sequence x m prime Chekhov homology k x m Chekhov homology x m double prime, and then the same thing but with the k possible. And finally, most important and the technical part of the proposition is the following. if E is injective, then the positive Checker homology and injective module E are all 0. This is for any k greater than 0. Okay. Yeah, while formulating this statement, I was thinking really that M is a finite. I don't think that I'm going to use that M is finite, so M actually could be any other module. Let's see this. Okay, so the first part. Zeros check homology for the sequence X and the module L. Well, remember the complex, the stabilized Kazoo complex, the zeros homology will be just the kernel of the map from M to the sum of its localizations. Yeah, I didn't mention this, but it follows from how we derived this presentation of the stabilized Kazoo complex that, of course, all the maps here is just maps to the localizations, and then you just take the sum of these maps. Direct sum. Okay, so this is more or less just looking at the complex. You'll get this is kernel of this map. Now let's be more specific. So in this kernel we have elements W such that xi to the t W is 0. So for some t positive and I between 1 and c. So this is more or less what you get if you know that in each localization and each of the xi's W will give you 0, right? So the multiplicative system is just the powers of xi, and using the definition when the fraction is 0, you'll get this xi to the t times W to 0. Okay, now this we can rewrite as all the W in the M such that ITW is equal to 0 again for some t positive. And so we get this condition for the generators, and of course this is equivalent to get this condition for the whole ideal. And finally, this last thing is by definition, well, this is by definition gamma I, but we know that the gamma I is exactly the H0I. And that's the proof of the first part. The proof. Yeah, and you can see that it's not important here that M is finite. Let's also check that, well, for part 2 is also definitely not important, so I'm removing this. M is an R module. Okay, for the second part, we know that whenever we have a short exact sequence of modules, we have a corresponding short exact sequence of the Kazoo complexes at the moment not stabilized. We look at this thing when we discuss Kazoo complexes. So this we have. And then what's left is just take the limit, right, with respect to t, and then you get the stabilized version. So this is quite easy. And definitely doesn't require M to be finitely generated. Okay, so this finishes the proof of 2. Now we need to do part 3. Okay, 3. Well, if you look again at the definition of the Kazoo homology, you can see that if you apply Kazoo homology to a direct sum of modules, then this will be the direct sum of the corresponding cohomology. And since the ring is not theorem, we know the structure theorem, we can say that it is enough, so it is enough to show that we have this vanishing HKX for the injective hull of the R modulo P. Right, because any other injective module is just direct sum of such injective modules. Maybe it would be better if I be on the right. Okay, now since we know that if we localize, we'll get the same module, we can, without loss of generality, assume that the RP is a local Noetherian ring. And the injective hull, by what we proved in the lemma just before the statement, I can as well write this as the direct union over n of the En, or I can write this as the direct limit of the En. Right, so here En stands for the bunch of elements in the E such that they are precisely annihilated by the P to the N. So then Kazoo cohomology of the injective hull of R modulo P, I can plug in this limit, use that the limit is exact, and pull it out and write limit of the cohomology, check cohomology of the ENs. But what we can say about this En? Well, the length of the En is finite. Right, so this is a modulus of finite length. So again,
Why is it true? Why is
well, the length is finite if this is supported on the maximal ideal, right? But clearly this is supported only on the maximal ideal P.
Yeah, why it's true?
Why it's supported on the maximal ideal P?
Yes.
Oh, well, essentially this is a En is a module over R modulo P to the N. Right, so P to the N is kind of in the annihilator, right? So the up to radical P is precisely PP will be precisely the support of the unique associated prime. So it is enough to show now that this local cohomology are equal to 0 if the length of M is 0. Right? If you know this for the if the length of M is finite. So if we know this for finite length modules, we know this for all injective hulls, and then we know that. Well, we know this for this particular injective hull of the R module maximal ideal. That's enough. Okay, but if you want to show something for modules of finite length, it is enough to show. Well, if you want to show some vanishing, right? It's enough to show. So it's I. It is enough to show. Here there's a little bit terrible notation. I want to apply this to the K, the residue field. maybe not to confuse with the index. Let me just write R modulo P. Okay? If you can show that this is true for the R modulo P, then this will be true for any modulo of finite length. Well, that is because we can do this the inductive argument. So this is just an extension of one module of finite length with another module of finite length of the smaller length. And if you know this for the length 1, know this for length 2, know this for length 3, and etc. for any finite length. Using, of course, this sequence of homology, right? This will be finite length but smaller length, finite length but smaller length, so by induction hypothesis. This term will be 0, this term will be 0, this has to be 0. Standard argument that I think we've done several times. Okay, so now we consider two cases. Consider two cases. So in the first case, say case 1. So there is an index I such that xi, well, xi is not in P. Well, since we go to the localization, we can say that xi is a unit. Xi is a unit, but if the xi is a unit, then in the corresponding causal complex, so for R modulo P, this causal complex is acyclic by general properties of causal complexes. And if this any causal complex is acyclic, direct limit is exact, so the limiting complex is also acyclic.
One of the elements of the unit, then the whole causal complex is acyclic.
Well, just look at it. Well, you can prove it, it's a very easy statement, but the proof is also given in this section what causal complex is. Well, the idea is that, well, it's quite clear that the homology of causal complex are supported on the V of the ideal, right? And if there's a unit that the V is not, it's just the an empty set. Okay, so that was the first case, and there is the second case, of course. In the second case, we assume that x1 up to, what was that? xc, I think, yeah, fixed notation at the beginning of the section. xc, this is subideal in the P. Right, but in this case, I claim that I can explicitly compute the stabilized causal complex for this axis with coefficients in the R modulo P. And this complex looks like this. I'll get 0, then in the degree 0 part, I'll get k. Well, k is R modulo P. R modulo P. And then all the other terms in this complex are zeros. There is nothing else but zeros here. Right? Do you see why the rest are just zeros?
Well, just localization by something that lies in the annihilator.
Yeah, because exactly we're localizing xi's which are in the annihilator. The annihilator is P. And with this observation, we finish the proof of this proposition. You can say that this is not very interesting proposition because we actually didn't prove that local homology and the Czech homology are the same, only in degree 0 are the same. But from this proposition, deriving the general statement is just a very easy exercise in the dimension shifting. So let me say theorem. Just to fix the notation. Let I be as before. 1 and 3. So this is ideal. M is an R module. So then the local homology of I, the module M, are isomorphic to the Czech homology for this sequence and module M. Okay. Proof. So by induction, okay. So case k equal to 0 is done. Previous proposition. So the base of the induction we already established. Now let's do the step of the induction. So for k positive, we take short exact sequence, say M. Now embed this M into injective module. We can always do this. For example, we can take the injective half of M, and then take some quotient N. So by definition, E module M and E is injective. We can always do this. Maybe in the minimal way, maybe not the minimal way, not important for the argument. And then just do the standard argument, which is in homological called the dimension or degree shifting. So if I want to compute the Czech homology with index k plus 1 for the module M, I know that I have a long exact sequence. I know that on the injective modules, this homology theory give me 0. So this will be the same as the Czech homology with the index k, but for the module M. Okay. Look at the long exact sequence and use the fact that on the injective modules we have 0, so the long exact sequence kind of separates in such isomorphisms for positive k, for each positive k. Now by the induction hypothesis, I can replace this with the local homology with the index k and the same module N. And this I can identify with the h k plus 1 I of M by the same reasoning as before, right? I just look at the now long exact sequence, but now for the local homology, and I know that for local homology on any injective module gets 0. This is just a general property of any right direct factor. Hence, this is the end of the proof. Okay. Now I have two definitions that I need to give. The definitions are kind of independent, they define different things, but they go one after another, and there are no statements between them. So let I in R be an ideal. The arithmetic rank of I is, the standard notation is ARA of I, and this is just the formally speaking infimum over On such that there is a sequence x1 xn in the R, and the radical of the ideal generated by this sequence is equal to the radical. That's the formal definition, but the formally you can see what's going on. You're kind of interested in minimum number of generators of this ideal, but up to radical. If you can go to another ideal, if it has the same radical, you can try to count how many generators you need to that ideal, etc. So that's an arithmetic ring. And there is another definition, not at all related to this definition, but they are related kind of by the next statement. So I need two definitions to formulate the statement. So definition, the homological degree not degree, the homological dimension of an R module M with respect to ideal I is the following. So the notation is CD, homological dimension. It depends, or actually it kind of depends on the ring, it depends on the ideal, it depends also on the module, and by definition this will be the infimum of the K such that HKI of M is not equal to 0. Wait a second. This is not infimum, this is supremum. So kind of the maximal index such that local homology are non-zero. After this index, all local homology are 0. Yeah, and maybe just as a remark, for local Noetherian ring Rm, we can use simple notation. So we set homological dimension with respect to the maximal ideal in M. This would be just like, no, that way around. The homological dimension of M, this would be just by definition, homological dimension with respect to the maximal ideal. This a standard kind of notation. If the ideal is maximal ideal, we just don't write it.
A question. About the Taylor theorem. Did you prove that for injective models the homology of local homology is 0?
Sure. We don't really need to prove this. This is the general property of linear vector factor.
Linear factor.
Okay, so with these two definitions, now I can formulate corollary from theorem. Let's say this is corollary 1. These two parts. So first part. Well, if this is a corollary, I'm going to assume the same notation as in the theorem and the same data as in the theorem. And the statement now is the following, that the homological dimension for pair I and M, this is less than the arithmetical rank of the ideal I, and this is for any R module M. Right? Well, the statement is that we definitely have the vanishing of the local homology if we go beyond the arithmetical rank. But this is true since we can compute this local homology using the Checker homology, and in the Checker homology we have an explicit complex, and it stops when we reach the degree which is equal to the number of generators.
But why is there less equal? Oh, why it's not less equal?
Okay, so there is one observation, and the second observation again that just immediately follows from the identification of the local homology and Checker homology is that we can kind of explicitly always compute the top local cohomology and this will be the M localized all the x's modulo the sum over I between 1 to c of the images of the x1 xi minus 1, xi is missing, xi plus 1, xc. Well, just nothing else but looking at the co-kernel of the last map in the Czech complex. Okay. Okay, so now kind of another proposition, which is well, it's not really an independent proposition, since well, it's based on the same idea that I can compute local homology using stabilized Czech complex. I'm going to call this corollary number 2. So let, as before, or no. Let R and S be material rings. Phi from R to S is a ring map. And we have modules. So N is an S module, and M is an R module. Okay, so then first, sometimes this is called the independence of base for the local homology. Independence of base. And the statement is that if you compute local homology for the ideal I and the module N, right? So here N is an S module, but I can automatically consider this as an R module if I just restrict the scalars along map phi. So this can be identified the local homology for the extension of the ideal IS of the module N. Well, there is no notation for the ring in the local homology, but this is kind of over R, this is over S. And the second part of this corollary is the flat base change. Well, in the base change is more like algebraic geometry. In algebra, probably better to call this flat extension of scalars, something like this. Anyway, the statement is the following: if phi is flat, then taking local cohomology of the module M and then taking tensor product with S is isomorphic to the taking local cohomology for the extended ideal IS for the module which is M tensor with S over R. So in particular, local cohomology commutes with localizations and completions. And this is the reason why one of the problems in the assignment 4 need to be changed, because it's so easy. I know it's so easy to actually prove this on the lecture. But there is a problem that we can, the S is just a relation of R, prove that this is true. Just a very special case. Yeah, and the whole corollary is not so hard to show, just more or less direct computation. For the first part, we'll look at the stabilized causal complex. Maybe not stabilized. Yeah, let's do this not in the not stabilized version. With the diffusions in N. Well, we know that, and then just take a look if you prove this for the non-stabilized version. So then we can present it like this. Right. So then I just, using conservation property for the tensor product, keep the same complex. Plug in tensor product over R is S, and tensor product over S, M. So these two things are isomorphic. But now, using associativity, okay, like parentheses here and move it here, but by the associativity to tensor product, I can replace this with the causal complex for the sequence phi of x t. Doesn't matter where I write t. Tensor product over S with M. But this last thing, of course, can be identified with the phi x t. And now we just need to look at the homology on the left-hand side and the right-hand side and see this precisely the statement which is independence on the base. Okay, for 2, it's more or less a similar argument. So complex is not just using the fact that the tensor product is a flat module, is an exact function, hence it can be used with taking a homology. So complex is, yeah, and here, to finish one, I can say that take limit and the homology. Okay, so for the true complex is the k x t m tensor over R with S. And complex that I obtained by the extending everything to the S. Well, yeah. So first of all, well, this is just the same thing. Complexes, which first complex is this one, right? And yeah, so complex, let me change this. This complex has the same cohomology. Same cohomology as complex k x m. Well, it's not precisely correct, so the same cohomology as cohomology of this complex tensored with S. Oh, you see the main difficulty here is just to formulate what I want to say, but I guess this will be talk with more or less trivial. We have one complex, we have another complex, and the difference between these two complexes is just there's a product with S, which is flat, and that can be used with taking cohomology. If you take cohomology, you'll get stating homology. Okay, so that was corollary 2. Now, the last one. So let M and N be our modules, and M is I torsion. Then we have three observations. First, I think that is something that we already discussed. If you look at the cohomology, then they are all zero. So for any index k positive, true, or just a special case, hki of the gamma I of M is zero, since gamma I of M is torsion, and 3 hk sub I of any module. In the second statement, there should be not M but any module, not necessarily torsion. This is why I need two modules, and it's just one torsion, one is not, one is just any module. So finally, third part, if I want to compute cohomology of N, this is isomorphic. This is again for any k positive. So the third part, cohomology of N, can be identified with the cohomology of the N modulo the gamma sub I of N. So you can quotient out the I torsion, and the cohomology, high cohomology, are still the same. Okay, so essentially the only thing that requires a proof, I think, is one, right? Two and three are just two very trivial observations. Do you see why one is true? Let's take a short pause and
What isn't one we proved?
No, we did a proof. We asked a question and I said this is the answer is positive, but I never gave you proof.
Ah. Ah. Ну, это из того, что у нас там укажуливый комплекс, или из того, что он там...
No, that's a right idea. You can use this stabilized Kazoo complex to compute the cohomology. Well, let me give you the main claim. So to prove one, I claim that if you look at the stabilized Kazoo complex, then this will be a very simple complex. Do you see what it will be? Of course, in the beginning we'll get 0 and M, but how about the rest? The rest is just 0. There is nothing else but M in the degree 0. Right, and why the rest is 0? Well, this is since all such localizations are equal to 0. Any x in I. So I like to think about it geometrically. The localization is kind of the restriction on the open subset which is complement to the corresponding hypersurface, and this is, and M is I torsion, so it's supported on the vanishing set of I. So this is definitely something that doesn't intersect. So 2 and 3. I want to say this is clear. Okay. So proposition, well, if I want, I can call this another corollary. It's also based on the presentation of the local cohomology via stabilized Kazoo complex. But we have here a little bit more assumptions. So let I generated by the x1 x c inside our B an ideal generated by a regular sequence x1 x. Oh, maybe don't need if I'm saying that this is regular 6, I don't need to write here, but anyway. So now I additionally assume that the sequence that generates the ideal is a regular sequence. This is more information that I haven't had before. So then I have a formula for the local cohomology. So hk sub I of M can be identified with the Tor over the ring R with the index C minus K. So the first coefficient of Tor is M, and the second coefficient of Tor is kind of the top local cohomology of the ring R. Okay. Proof is again quite simple. Right. So let's look at the stabilized Kazoo complex. Well, what we can say about the cohomology of this complex? Well, the top cohomology is precisely this thing, right? But how about the other cohomology?
The cohomology is H and K of M.
Yeah, but what we can say about this cohomology?
Yeah, is this regular sequence R regular sequence or M regular sequence?
This is our regular
R
sequence.
regular sequence.
So let me say this is a regular sequence. See,
Since it's regular sequence, it's like
R.
well, it's a cyclic.
Yeah. So this complex is only top cohomology, and there are no other cohomology because the local cohomology, which we know that is the same as the Kazoo cohomology, vanishing for the indices less than depth. Depth in this case is C. So this thing is a flat resolution of the HC sub I of R. Okay, now looking at the check homology. Check the homology of the coefficients of M. We know that this is by definition just the stabilized Kazoo complex with coefficients of M and can take the homology, but we can also write this as a product of the stabilized Kazoo complex and M. Right? But this is now the stabilized Kazoo complex is a flat resolution. So this is just a thing that computes Tor, but we just need to be sure what the correct index is. C minus K is the correct index. Okay. Now this looks like kind of innocent formula at the moment, but this will be our source of the local duality next week. Because you see that, and we know that there is a general situation. For example, when this is a Noetherian ring, this is finitely generated module, this second version of the X-Tor duality. If I can present this as the matrix dual of something, I can move this matrix duality outside and get X. So we will get isomorphisms that local cohomology has some matrix duals of the X. So this is the plan for the future. Okay. So not just out of curiosity, but quite kind of important formula. Okay, and this is the last formula in this section. So next section, 5.3. This is the local situation of local cohomology. So local cohomology with the port in the maximal ideal. So it means that here in this chapter we're going to assume that ring is local noetherian ring, and the ideal I that we consider is the maximum ideal of this ring. So let's prove the following lemma. Let Rm be a local noetherian ring. So then we can explicitly compute the torsion factor gamma sub m on the injective hull of the R modulo P for some prime ideal. Okay. So let me just write an answer. So this is the injective hull of K if P is equal to the maximal ideal, and 0 if P is not equal to the maximal ideal. And here I need to write it somewhere. So local noetherian ring, and P is in the spec of R. Okay, so this is an elementary computation. Okay, so let's see. If we have some W, which we assume to be not equal to 0, that's an element in the gamma sub m of the injective hull of the R modulo P. Right, so then by definition there is index, positive index t, such that m to the t times W is equal to 0. So we'll get an embedding of the R modulo m to the t. It's a submodule inside the injective hull of the R modulo P. Now, as before, we can say that there are different ways to say this. I'm not sure that what I'm saying is optimal. Well, support of the R modulo m to the t, right? So this is just a maximal ideal. This is the same as the associated primes of the R modulo m to the t. And this is just the set that consists only of the maximal ideal. Right? So this maximal ideal m is associated to this module. So m is in the associated of the injective of R modulo P, which we know to be equal to the P. Right? Hence, we finish the proof, right? Because m is an element in this set precisely when P is equal to m. Right? And in this case, we already done this computation. We know that the answer is just the same module of the injective hull. And if P is not equal to m and we have this inclusion, this is not possible. Hence, there are no non-zero elements in this injective hull R modulo P. So, module of this works, we finish the proof. Okay. So theorem. So let Rm be a local noetherian ring. M is a finite, now this is important, finite R module. So then the local cohomology modules H, K sub M of the module M, this is Artinian for any K non-negative, including 0. Okay, so proof. Let E with a bullet of M be a minimal injective resolution. Be minimal injective resolution of M. So then we actually know how terms in this resolution look like. So EI of M, this is the direct sum over over B in the spec R of the injective hulls R modulo P, bus number mu I, depending on the prime ideal P and the module. Okay. So essentially, let's take this minimal injective resolution of M, right? And then we apply functor gamma sub M to this resolution, right? So we want to get the conclusion, and then we do this, the cohomology will be Artinian modules. But if you do this using this lemma, right? So we know that after applying this gamma M to this resolution, the only thing that survives is just maximal ideal. The rest are just zero. So this whole complex will look like this. We'll get 0, we'll get E to the mu 0 of M, and then we will get E to the mu 1 of M, etc. So here E is just a short notation for the injective hull of the residue field. Don't confuse this residue field with the index K. Unfortunately, there's this coincidence in the notation. But now, this E is Artinian, right? We proved this when we discussed Gorenstein rings. So this is Artinian, and this is complex of Artinian rings. And again, Artinian rings are closed undertaken submodules and quotient modules. So the cohomology, again, Artinian. End of the proof. And this is one specific property that works over in the local situation, but not in general. Okay, now let's prove another theorem, which is now in this case not very specific, but it's still useful to know. Theorem let Rm be a local Noetherian ring. M is an R module. Let's fix D to be the dimension of M. So then H, K sub M, M is equal to 0 for any K greater than the dimension of the module. Well, it's, I think it more or less follows from what we already know about the Kazoo complexes, stabilized Kazoo complexes. So proof. Well, first of all, we can set R prime to be R module, the annihilator of this given module, right? So now over R prime, this is a faithful module, and the dimension of the R prime is equal to the dimension of R. So we can, using the independence of the base, we can go from the ring R to the ring R prime. Okay, so let x1 up to xd be a system of parameters. So let me say this without loss of generality. Now I want to assume that the dimension of the R is equal to the dimension of M. Otherwise I go to this R prime. So in the system of parameters of R, I have as many elements as the dimension of the module M. So this is a system of parameters, and since the system of parameters, the maximal ideal is the same as the radical of the ideal generated by this system of parameters. And we know that we can compute local cohomology, now in this case for the ideal M, by going to another ideal which has the same radical. So in this case, I just go to the ideal, which is generated by this sequence, which is just a system of parameters. Okay, but now for this ideal, since I know generators of this ideal, I can identify this with the Check cohomology for the sequence. And I know that the Check cohomology are equal to 0 for any k greater than d. And this finishes the proof.
That's not true for not local
It is true, but it requires a proof, and this proof you'll be reducing to the local case. This is the problem that I want to give you in the assignment 4, that instead of that silly problem. Okay, so it looks like I have something like a couple of minutes, and the next theorem is kind of a heavy theorem, one of the important theorems, so maybe I postpone this to the next week.